I'm going to present part of what I did during my PhD. Basically, I'm going to present the geochemical side of the analysis I did during my PhD. So basically, is it working? Okay. So, well, I guess I don't have to convince you of that, but like, why is it important to study dust? But it has impacts on climate, atmospheric chemistry, biogeochemical cycles, and like inversely as well, there's the climate influence the amount of dust in the atmosphere. So there's like a complex interaction between all those compartments. And also, these interaction leads to a high spatiotemporal variability in dust deposition. And this high variability makes it a bit harder to understand like the climatic interaction between dust with dust. So another reason why it's a bit more complicated is that there's a lack of terrestrial archives. There's mainly marine archives, and like in terms of terrestrial archives, they're mainly located in Lurs area or in or come from ice cores, which are pretty isolated. So there's like large part of the Rio, several regions where there's no records, and so one of the options we can use to get a greater number of archives are peat bugs. So why we could use peat bug? Well, basically, peat bugs receive only atmospheric inputs. Mostly from nutrients and precipitation. They have high accumulation rates and like high resolution. For example, a mean of about 1,000 years per meter. They're largely distributed in the area, which with very limited records. So, and also they very easily dated because they contain high amount of sphagnum. So, and sphagnum has a high amount of carbon. So which is like the base of this project. Based on that, we wanted to characterize the spatiotemporal variability of atmospheric dust deposition in Eastern Canada. In there, it's linked with climate in the region, and some of the sub-objectives of the study were to reconstruct the atmospheric dust deposition fluxes during the late Holocene using litogenic element and rare earth elements, using peat bugs. Then after that, we tried, and I mean tried, because as I show it's partially working, but we tried to determine like the dust source using lead and neodymium isotopes, and ultimately we tried to characterize the relationship between the dust flux and the climatic variability during the mid and late Holocene. So for that, we selected 3 sites in Eastern Canada, so 2 located on the St. Lawrence North Shore, so the Bay Bug here, and Ile du Havre Bug, located about 500 kilometers further northeast from the other bug, and then another one in the James Bay region. So those 2 bugs were located more in the Greenland, Grenville geological setting, so more, this study site was located more in our Archean rock setting, so more negative neodymium local signal. So for that, as I said, we cored 3 peat bugs, subsampled them. We did multi-elemental geochemistry on these samples, mostly litogenic elements. The major element by ICP-OAS, trace element by ICP-MS, and then after that we did the neodymium isotopes and lead isotopes as well, using by MC-ICP-MS. We also did the particle size analysis, macrofossils, which I'm not going to present today due to lack of time. And then for the age-depth models, we combine lead-2 10 further surface samples with radiocarbon dating, and we use the Bacon program in R to make the age-depth models. And ultimately, we use the principal component analysis to try to confirm that we could use those litogenic elements in our peat bugs as a dust signal. So getting into the PCA analysis, as we can see, the three peat bugs show all the litogenic elements and the rare elements on the same component. They don't have exactly the same fraction of communality, but what it means mainly is that the first principal component of these analyses represent dust. And we know that, for example, titanium and aluminum are conservative elements, so it means that the rare elements are conservative as well in our profiles. So afterwards, going into knowing that, we did neodymium isotopes to try to identify the sources. Oops, those don't show up, but basically that's the atmospheric signal part of each peat bugs. So in green, that's the Lagrande bug in the James Bay region. In red, the Bay bug, and in black, the Ilzov bug. So here we have the epsilon neodymium through time, and as we can see, it's pretty stable over time once you reach the atmospheric part of the peat core. Here, the change here is mostly because there's still a contribution from local rocks and sediments in both the peat cores. For example, in the region of Bay and EDH bugs, the local rocks are around -20. And in the Algeder bug, which is in the Archean setting, the epsilon neodymium, well, I've got the profile a bit, but it's around -30 and -40. So we basically have a regional signal, which suggests that we have a common signal for the three peat bugs. But we couldn't identify the precise source for this neodymium, so it's probably coming from a mixing of sources, probably 3 or more, but we couldn't precisely identify them. So it's a common signal, pretty stable over time during the late Holocene, so this suggests that there were probably no important changes in sources, and that in our peat bugs, in this case, we cannot really use them as a record of change in wind direction, or there were just no change in wind change in wind direction during this period. So moving to the dust flux, we reconstructed the dust flux in the three peat bugs as well, using rarer elements. So here is the Bay bug in blue, the Algeder bug in yellow, and in green, the EDH bug. So we have mostly, the signal is mostly stable before 3,000 years. There's a large increase over the last 1,000 years in the Bay bug. Some more variability as well over the last 3,000 years in the Algeder bug, and basically no clear signal in the other bug. Which we think that the discrepancies we see between some of these records are due to local factors, like for example, the EDH bug is located on an island surrounded by a tree ring, which probably intercept part of the dust, which could explain why the flux is so low and not as variable. And here, the Algeder bug is located in a region affected by frequent fire. And I've put here the charcoal accumulation from another study by Gabriel Magnan, his corporate et al. So basically, most of the period we have high dust fluxes in the jitterbug roughly correspond with peaks in charcoals. So the fire probably have an influence in the region. As for the but still, like most of the peaks in dust and as well as the fire and in the bay bug as well, the peaks in dust occur during cold periods in the region. Oh, okay. So basically what we think is that there's some link with the incursion of Arctic air masses in the region, because like most of the fire dynamic, it was proposed that they were coming from a drier incursion for the fire as well, and we know that there was a change in the polar front during that period. So going into the conclusion, like we presented the first dust record to our knowledge coming from peat bugs in North America. Eastern Canada peat bugs cannot be used as a tracer of wind direction. It's more a wind intensity record or change in land cover. There's no change in the dust source during the studied period, or at least not large changes. The dust peak occurred during cold period, and there's a great importance of local factors affecting the dust record in our region. Mainly site selection is important for that, and then I think we have to take into account fire as well, which is not done that much, I think, right now. So, thank you.
You said you didn't identify a specific source.
Yeah.
From the neodymium isotopes, but that kind of isotopic composition would be typical of a lot of Cenozoic rocks, Oligocene and Miocene rocks on the Great Plains, which are potentially major dust sources.
Sorry, I didn't get it all.
The neodymium isotopic composition that you showed,
yeah,
it was like -12 or -42.
Yeah.
That would be typical of a lot of Cenozoic rocks on the Great Plains that are known to be major dust sources in the Holocene and Pleistocene.
Yeah. I guess, but still they're pretty similar to sources from the Appalachian as well. So it's not clear exactly where it comes from, but and we cannot really do strontium isotopes in peat bugs, so we couldn't like use strontium isotope as well to better distinguish the source. So. Yeah, we did, but I think it's even less. It's even harder and less distinct than neodymium, I think, in the region as well. So it's always around 1.20.
So I'm presenting this work on the behalf of an army of collaborators, and it seems the longer I take to submit this manuscript, the more analyses we get, and the more the list actually grows. But we're looking at a high peat accumulation event that we think is actually controlled by dust inputs. And so this is linked to the role that dust plays as a nutrient transport vehicle. So a classic example is that we have the movement of iron and phosphorus-rich dusts moving from the Sahara and fertilizing activity in both the Atlantic Ocean and the Amazonian rainforests. But I've noticed that dust people like to spend a lot of time in arid places, and so today I'd like to make a little bit of a case for spending time in the northern latitudes. And so first of all, they're usually wet and cold and miserable, so that makes fieldwork awesome. But they're also often previously glaciated, which means you've got a large amount of unconsolidated glacial material that can act as a possible dust source. There's also a lot of my favorite archive, which is peat bugs. And as Steve already introduced for us, the best way to think of them is actually like a green glacier, but instead of accumulating snow and ice, you're accumulating dead vegetation. And the kind of deposits we work with are atmospherically fed. As a consequence, the actual system, so it's a living system on the surface, it's one of the most nutrient-poor ecosystems on Earth. And that's going to be important when I get further into the story. So our story takes place in southern Sweden. And the location or the formation of the landscape is actually really interesting. When we had the retreat of the Scandinavian ice sheet, this area was actually covered by a massive ice lake. And that's what you see modeled here with the white dashed lines. So we think that this lake can have extended something like 165 kilometers north to south. When you had isostatic rebound, you had a tipping of the northern end, and the lake drained via the southwest there. And so today you see remnants of the lake in the form of these lakes that are in the southern portion of this map. As a consequence of the draining, however, we have a now exposed lake bed. And so wind started acting on this lake bed. And believe it or not, what you see in black here in this map is all sand sheets and sand dunes. So we actually have, for instance, this deposit, which what we can see is actually something like 3 meters exposed dune system, but it could be much deeper. This lake bed also provided a very nice substrate for peat to start accumulating, being low and flat. And in the area, we have something like 300 square kilometers of peat. The area that we work in is up here, this big dark green clump. And that's actually in a national park called Stora Mosse. And if you translate it from Swedish, it means the Great Bog, and not in like the Trump sense. It is actually a great bog. It covers 77 square kilometers, and it's been studied for decades. So we know a lot about the hydrological development. We have pollen records. And so we decided that this was a place for us to start doing a bit of paleoclimate work. So we take our Russian core, and we retrieved 5.5 meters of peat, and we subsample it 1 centimeter slices. And at this site, that works out to about 16 years for each sample. And in the beginning, we were really interested in looking at effective humidity, so how wet it is, which is more like a local factor, and how that links up to dust, which can be local, regional, or global. As we got further into the dust story, though, we realized that the organic matter, there was some interesting things happening there. And I won't present any of that today, of course, but that's also another line that we started working with. And in terms of how we actually deal with all this data, we worked a lot with PCA, but we also use something called change point modeling, which helps us pick out significant shifts in temporal records. So the first phase of this paper, or this site, was to set the paleoclimatic framework. So what you're seeing here in blue is the peat accumulation rate as it changes over the last 9,000 years. And because I'm going to go on the assumption that a lot of you don't work with peat, a normal peat accumulation rate for this kind of deposit is somewhere between 40 and 50 grams per meter square per year. And if you're paying attention, we're looking for a high peat accumulation event, and you can see 5,000 years ago, we have an exceptionally high event. When we do our PCA of something like 36 trace and major elements, the first PC pulls out the combined behavior of our typically dust-related elements. And then we have indications of dustier periods. We also use the europium anomaly as a source change indicator. So based on this data and a lot of complementary data, I'm just showing you the cream at the moment, we could identify several dust events. So we have 3 events that we identified as high dust deposition rates, and we've later gone and quantified this using elemental mass accumulation rates. And then we identified dust event 2, which is a period when we have a significant source change. And if you're really quick, you'll see that DE2 lines up nicely with our peat accumulation increase. And I should say that the sources of the dust are continually changing over time, but this is the most significant shift. And just to give you a bit of paleoclimatic context, I'm showing you the hematite stain grains from the data of bond, so the bond cycles. And what you can see just prior to our accumulation event, we had very cold and dry conditions in Scandinavia at the time, and then we have a rapid decrease. And so we would have a re-wetting and sort of a warming of the system, which can explain this peat accumulation event. However, the magnitude of this shift is so great that we think there has to be another mechanism involved. So the second part of this study, the second paper, got into the real nitty-gritty of what the chemistry is actually telling us about the mineralogical composition of the dust. So here we have our peat accumulation rates again, and now I'm showing you the light to heavy rare earth element fractionation, and middle to heavy rare earth element fractionation, and then again the europium anomaly. And what you can see is in dust event 2, we have a shift in both our light and light and middle rare earth elements. And so they're kind of embedded in a longer term change, but this change that we picked out using the change point modeling, which is actually this colored line, whereas the original data is in black, you can see it is quite sharp on across that boundary. If we put it in biplot space, and I've got about 1,000 more biplots where these came from, but I've decided to show you, again, the fractionation of light and middle rare earth elements, the europium anomaly, and here I also put in aluminum, but I could have just as well put in total rare earth elements. But if we think about what these changes in these ratios actually means, the rare earth elements are hosted in most by the phosphate minerals. And then the europium anomaly, europium is able to substitute for calcium and strontium, for instance, in plagioclase. So we can often get an increase in the europium anomaly and still have low concentrations of other rare earth elements. But we've also seen that the europium anomaly increases in unweathered material. So increases here, we're thinking it's plagioclase feldspar and unweathered minerals coming in. Clays tend to increase with aluminum and total rare earth element concentrations. So what you can see is for dust event 2, which is shown in purple, and those filled triangles are actually early in this dust event, that this dust event 2 has very distinct chemistry compared to the rest of the profile. And so we have probably the input of phosphate minerals and plagioclase. And if we look at this back in our temporal perspective, we would see increase in phosphate minerals and phosphorus input. And then with the europium anomaly, we know because it's plagioclase, we likely have calcium coming in, but we probably also have potassium feldspars coming in at the same time. And again, this is based on several pieces of evidence, not just these profiles. But essentially what we see is that when we have this massive peat accumulation increase, which is likely from a re-wetting and a warming of the system, we also have an input of phosphorus and potassium and calcium into the system, which are both major and minor nutrients to the system. So we think that we sort of had an explosion in productivity, basically because we had a perfect combination of hydrology and dust inputs. And so probably most of you are thinking of, well, how good is your age model? And so I'm going to convince you on that. This is the age model from our core, and here you can see that event 5,000 years ago, and we've dated the crap out of it because we really want to make sure. We also have another profile from a PhD thesis from Stora Mossa as well, but again, you see they have that same increase. And the idea that we have is that these sand deposits could potentially be the source of this unweathered coarse-grained material that we see coming in at that time. And it kind of makes sense that it would be the closest source for such a coarse-grained input. And we also know that 5,000 years ago, things were a lot stormier in Sweden at the time. And just to prove this a step further, we looked at a deposit further down south, which also sits juxtaposed to a sand dune system. And again, 16 kilometers away, we see the same increase. So we're thinking that this is a really regional event, but we also think it's the perfect storm because we have the right hydrology, the right kind of deposits in the area coming together at the right time. But the implication is that we actually see a link between the dust cycle and carbon storage in northern latitudes. And although these numbers don't seem that impressive if you're a carbon person, I still think they're pretty impressive because it's like megatons. So that's a lot. But hopefully what I think, or hopefully I've convinced you actually, is that dust can be really important in temperate regions as well, particularly in nutrient-poor systems like peat bogs. Thanks.
I was wondering if you have consider, as Steve mentioned in his presentation earlier, the fire recurrence events into that could also release some of the dust influx.
So we've observed charcoal, but only furthest down in the record, not anywhere further up. And I should actually also mention that peat accumulation event, we think it's all sphagnum species. Some people have said, well, is it trees? But it's really sphagnum.
Yeah. No, but you could have had also some tiny charcoal that would reflect some fires in the, let's say, regional fires, for example.
We haven't looked at that, but we think we have a pretty good mechanism so far. But I mean, it's absolutely something that we could look into.
What do you think, like, if you would want to connect it to the global dust cycle, how would it connect to how the higher latitudes react to these kind of shifts in dust deposition?
Do you want to develop your question a bit? I mean, because this is just really a local event. So.
But then would you expect to see more of these local events globally in these conditions, under these conditions?
I think that this is a very special sort of landscape formation and development and special hydrology. And, you know, we get the re-wetting of the system at the same time that we get increased, or, you know, just prior to this increased storminess and then these sand dune systems that are sitting there. So I think it's a perfect storm. I don't think we're going to find such an extreme event in other places. But that being said, I think that dust is feeding productivity in peat bogs. We just can't detect it because the changes aren't that extreme like what we see here.
If I can comment on that, you can find those kinds of events, as you say, if you have the exact same conditions. So a store, a closed dust source, and a reactive peat bog. You see that elsewhere in the world. But you need those three conditions to have the event. Which doesn't mean that the event cannot be global, because at the end, it's the storm, and the storm is climatic, so you can have that elsewhere.
I think
But you need the dust source as well.
But you need a certain, so the important thing is not the amount of dust, it's the character of the dust.
Yeah, I was wondering if the vegetation cover was changing as well at this moment.
Around the bog, or do you mean?
Yeah, or around the dunes, if it was less covered or more covered.
My assumption is that we would have some drop in the coverage because something has to expose them. But we don't actually know that. And we're actually going to, so there's a dune system that's transecting Stormosse. And so in September, we're going to go and have somebody start working on a record that's just proximal to the dunes and see if the signal is more amplified there.
Hi, I'm Chuxian Li. Today I would like to share a little bit story about Holocene dust composition in the Indian Ocean, inferred from Amsterdam Island peat geochemistry. So thanks for the good explanation from Steve. I can skip most of the content here, but I would like to highlight one thing about the dust. Dust is, the record of dust is very important as it could identify the flux and the change of the source of air-lying materials. And then the peat. Thanks for the explanation from Malin. So here I just want to mention one more thing. Most of the case, peat starts to accumulate at the top of a dry lake. And then this part we call, as you could see here, the green part here, we call it minerotrophic, which will be influenced by the underground water and atmospheric input. And then step by step, when the peat accumulates above the underground water, it becomes the umbrotrophic part, which means that it is only fed by atmospheric input. And as we can see in this top left figure, peat has a wide coverage on the Earth's surface. And currently, peat has been abundantly used to monitor the past atmospheric pollution. Less attention has been given to the pre-anthropogenic signals, especially in the southern hemisphere. Like the previous two presentations, both of them are about the southern hemisphere. So southern hemisphere, here we go. In the the graph on the bottom right, as we can see here, the green star represent for the peatland, and also, and then the blue circle represent for the marine core. And as we can see, there is not so much dust records from the pits in the southern hemisphere, especially in the Indian Ocean. But you can see a lot of marine cores in the Indian Ocean. You might wonder, well, a lot of dust record from the marine core being done, and what are you doing here? Why do you still want to do some dust in the southern Indian Ocean? Yep, most of the records from these marine studies, they focus on glacial or the cycle of the interglacial glacial period. And the Holocene dust records has relatively low resolution, but we would like to understand the cycle of the dust in the southern Indian Ocean with relatively high resolution. So we have collected one peak core from Amsterdam Island. Before, some of my friends asked me, hey, what was your study site? Amsterdam Island? And then most of them respond to me like, in the Netherlands? Well, nope. It is a little bit far away, like 12,000 kilometers away. And so as you can see on the top left figure, Amsterdam Island is located within the westerly wind belt, and the nearest continent is South Africa. So we have collected some peak balls at the center of the island, and then bring them back and try to play with it. So we subsample the pit into several pieces and for different analysis. And for the geochemistry part, we digested the samples in the clean room, and then use the ISP mask to get the data. And our peak core is around 5 meters long, as you can see at the first figure, and then followed by the density. The third is ash content. The final one is the mean grain size. So from the core itself, plus the density and ash content, we know that there is a transition part in our core from minerotrophic into ambrotrophic. Then our chronology is made based on 10 macrofossil 14 carbon dating and 15 to 10 lead dating. So, and then as you can see in the y-axis, and the age of our peak core is around 6,600 years old, and then the accumulation is around 0.76 millimeter per year. Well, not that low resolution. And here, as you can see, the graph, the black curves represent for the concentration, and then the red curves represent for the dust flux, which are calculated by the equations in the blue books. And so, as also the two previous presenters have tell us what is titanium and rare earth elements, so I don't need to repeat them. But here, I would like to point out things like the pattern of the titanium and rare earth elements. They have quite similar patterns. And so here, thereafter, I mainly talk about the dust flux by rare earth elements. As you can see, there's the second graph. We can see some obviously pit in some period. We might wonder, so where did the elevated dust come from? Are the signature, the rare earth element signature in this elevated dust very different from the sample with no peak, the dust flux peak? So, and let's have a look at the rare earth element pattern. So we have plotted 104 samples from the Amsterdam Island pit, and in the they are presented in the gray curve. Wow, there are not so much difference. Seems a little bit not that interesting. And here we mainly talk about two most possible dust contributor: the local rocks, and then the nearest continent, South Africa. So if we try to plot the rare earth elements pattern from the rocks in Amsterdam Island, we got the pink curves here, and then the South Africa dust are presented in the blue curves. Here we might say that, okay, the dust in Amsterdam Island peatland is kind of a mixture of these both sources. So for more information, we need to come to the second proxies, the epsilon neodymium. As you can see here, the blue dot, they are the epsilon neodymium. And if you have a look at the right y-axis, you can see that our epsilon neodymium varies a lot, from around minus 7.5 to almost 1 along with the time. So at this time we were thinking, so what the epsilon neodymium signature in the local and far away? And if we have collected many samples from the island, which is shown in the red color. And then we got the average data of minus 0.4. And then if we follow the paper by Gatrina-Jantella, and we have an idea that, okay, the epsilon neodymium in South Africa is really negative, around minus 20 or even more. So let's come back to the figure. As you can see here, in the blue line, that is the epsilon neodymium signature in the local rocks. But you can see most of our data, they are more negative, more close to South Africa. So let's assume that it did have a lot of dust come from South Africa. And then it means that the grain size of the particles should be very fine, like less than 12 micrometer, because otherwise it couldn't transport it over 1,000 kilometers away. So, and then let's have a look. The most negative epsilon neodymium signature samples. So the gray bar, they are the grain size. The proportion of the grain size less than 12 micrometer, as you can see here. And then the sample into the blue ellipse, they have more negative epsilon signature, but at the same time you can see the proportion of the fine particles, they are quite high, around 50%. And in the recent part, like at 19th century, even more negative, with a huge proportion of fine particles. Sometimes it reached 100%. So it seems like in this period, there is more particle available in South Africa, or there is the westerly strengthened. Otherwise, the dust couldn't come from such a far away continent. So, and then I tried to have a look at the records from other literatures about Africa to check how about the climate there corresponding to our results. So here, I would like to point out one obviously abrupt climate change in Africa. It's around 2000 BC, which is shown in the red line. The Thompson, he published this paper in Science, and then he pointed out that there is a abrupt climate change from humid into cold and into cold and dry climate. And at this time, interestingly, our dust flux increased a lot. And then it seems like, correlated to the climate change in Africa, but I'm still on my way to understand my results. So I'm the second year of the PhD, so I still have some time to finish my story. And what I conclude for this presentation is, okay, the chronology is is okay and give us like 6,600 years age. And then the rare earth elements and the absolute neodymium from the dust particles suggest a mixture of the local and South African source, but at different time, the proportion of this source contribution is different. And then the final one is the variations exist in the dust flux, absolute neodymium grain size suggests something changed in the particle availabilities in South Africa, or is the change of strength of westerlies. So thank you so much.
You said that the explanation of the isotopic composition is because the movement, the polar movement of, or in fact, the contribution from southwesterly winds. But how do you think that probably most of the model indicate that during Holocene, the southwesterly wind move polar, and that's probably it never touched, or it were not a strength over the southern part of South Africa?
Yeah, I also checked the literatures before, but yeah, good idea, but I haven't really have clear like information about this. Yeah, I think there is some papers about that, but I haven't really have an idea about it. Yeah, but it can have some like a shift of the westerlies, and then to have so the dust is sometimes it doesn't come from South Africa but elsewhere, but yeah, that it happens anyway.
Your comment? Question?
I'll make a comment here, if I may.
I'm sorry.
Actually, the models show that the South American source reaches into the South Indian Ocean, more so than the South African source. So you may want to check the isotopic signature of South American sources. If you
so yeah, here I would like to, yeah, thanks for the suggestion, but here I would like to point out one thing. Actually, we did make money, like compare the signatures from South America. And, but the absolute neodymium signatures, they are around 0 and 4. They are between 0 and 4, but as you can see here, our data are more negative. And if they are 0 and between 0 and 4, if we do have some dust come from South Africa, and then they should have the signature of the epsilon neodymium here, but we don't have it. So it's interesting point. No? The epsilon neodymium signature, the dust, because that is the data, that is from one paper studying the ice core in Antarctic. So from this point, we don't talk about South Africa. South America.
So, hello everyone, I am Eléonore Resongles. I work at Imperial College London on the reconstruction of dust deposition during the Holocene in the Falkland Islands, also named Las Malvinas, and they are located in the southern Atlantic Ocean. So, in the southern hemisphere, the main sources of dust are Australia, South Africa, and South America. And for the southern Atlantic Ocean, South America, according to current model, are the main dust supplier. So within South America, Patagonia is considered as the main dust source, and it is likely to be the main dust supplier for the Falkland Islands, because they are located downwind the Patagonia at about 500 kilometers. But other sources not located on northern place could also contribute to the dust deposited in Falklands, as well as Andean volcanoes, which could be an important source of volcanic ash for the Falklands. So in this region, the dust deposition, the dust emission and transport is mainly controlled by the southern westerly wind belt, because it controls the climate and the circulation pattern in southern South America. And today it extends over 300 kilometers, 3,000 kilometers, and the Falkland Islands are located in the core of the belt, of the actual belt. We know that from paleoclimatic reconstruction in South America, that variation of lateral position and threat have happened during the Holocene. And this variation could have influenced the transport of dust from South America to the Southern Atlantic Ocean. In particular, three periods of high dust fluxes have been identified in Patagonian peat bogs, and they have been related to glacier fluctuation, which control the availability of particles, and also to periods of stronger western ice. However, the lack of terrestrial archive in the Southern Atlantic Ocean limits our ability to understand the link between dust and climate in this region during the Holocene. So in this context, the Southern Sun project aimed to use a peat archive from the Falkland Islands to reconstruct the history of dust deposition during the entire Holocene. So thanks to the other speaker, I don't have to explain how peat are a great archive to do that. And we aim more specifically to identify the local versus non-local sources that include mineral dust from South America, but also volcanic ash, and to quantify the fluxes of dust deposition. And in fine, we want to link our paleodust record to change in atmospheric circulation in this region and climate also in South America. So it is the beginning of the project. So today I will present the first geochemical results we have for one peat core and assess the potential of this peat record to reconstruct the history of dust deposition. So 3 peat cores have been sampled in 2012 in the northeast of the Falkland Islands. And today I focus on the Kingris peat site. It's a peat bog with an extent of about 1 square kilometers, located in a broad and shallow valley. The core is about 4 meter depth. It's where we have reached the underlying sediments. And as Chuxian has described, it has been sliced and analyzed for inorganic chemistry. So first we have established the chronology of the peat sequence. For now we have 6 radiocarbon age. So the basal peat gave a radiocarbon age of 13,000 years old. So that means we have a record for about the last 15,000 years. That covers the late glacial and the entire Holocene. And the age depth relationship is not linear. We have an important increase in apparent accumulation rate around 8,000 years. But we need more radiocarbon age to confirm this trend before to conclude on that. So the general characterization of the peat core. The density is comprised between 0.1 and 0.2 with slightly higher values at the bottom of the core and in the upper part. These values are quite high compared to ambrogenic peat, but it's consistent with the character of the peat, which is well decomposed and quite compact. The ash content above 3 meters is comprised between 3 and 13%, with several peaks, which identifiable. It could correspond to increase in mineral dust deposition, or also to tephra layers from underground volcanoes. And below 3 meters, the ash content increase together with a decrease in carbon concentration. So we have a dilution by mineral matter, probably an input of local sediment. Before to interpret the pit core in terms of atmospheric signal, we have to check that post-depositional process doesn't affect the mobility of elements in the profile. So if we look at these 4 lithogenic elements, aluminium, titanium, scandium, and yttrium, we can see that they exhibit the same pattern with quite steady concentration above 3 meters, excepting the depths which correspond to the ash content peaks. And again, below 3 meters, an increase in concentration which corresponds to the increase in sediment content. The correlation between all these lithogenic elements and the ash content confirms that these elements are well conserved in our pit record. So we can use them to assess the actual variation of other elements in the pit, in the dust fraction. Calcium and strontium profile doesn't exhibit significant increase in the bottom part of the core, so that suggests we have minimal influence of groundwater or sediment dissolution in the profile. And if we look at the rare earth element concentration, they are all correlated, including the cerium, which is a redox sensitive element and potentially more mobile in this environment. And again, the profile of the concentration follows the trend observed for lithogenic elements. So we are confident that rare earths are immobile in this profile, and we can use them to trace the origin of dust in this record. It will be probably more tricky to identify the atmospheric signal in the monoeutrophic section, since it's really dominated by the sediment fraction, but the embryonic fraction covers the entire Holocene. So if we plot the light sur heavy over heavy rare earth element fractionation against europium anomaly, we can see that we have variable signature in our pit samples. So the samples at the bottom of the core correspond to the signature of the basal sediments, but above we see variation with nourishment in light, it's an error, with light rare earth elements in the surface. And this variability suggests that we have different origin of dust in our pit core, and most of the samples fall within the range of signature found in Patagonia. Some of them are outside that, but before to conclude concerning the origin of the dust, we need to better characterize the local sources and to combine that with other tracer, in particular neodymium isotopes and lead isotopes. So I tried to estimate dust accumulation rate. It's of course the first accumulation based on our rare earth element concentration and our preliminary age depth model. And for the last 8,000 years, we have an average dust flux of 3 grams by square meter by year, which is lower than the background reported for Patagonian pit, but logic since we are faster from the sources. So to conclude, we are confident that we have a good record to reconstruct the history of dust deposition in the Falklands during the entire Holocene. The variation in rare earth element signatures suggests that we have different origin of dust. But it's only the beginning of the project, so we need to go into a deep characterization of the geochemistry to be able to identify the different sources and to improve the age depth model before to calculate dust fluxes. And yeah, we expect to be able to interpret that in link with changes in atmospheric circulation and climate in South America. And I thank you for your attention.
What's the peat composition?
You mean in terms of vegetation? Today, it's mainly Empetrum rubrum, so shrubs, and grass. And I looked at to check macrofossil in it with a specialist from NERC, but we didn't find identifiable macrofossils.
Okay.
It's mainly graminoids, and there is no sphagnum. It's not a sphagnum peat, yeah. Yes, it could be, we believe it's mainly Patagonia, but it could also be the central Argentinian desert. And also we have really to do the neodymium analysis for the volcanic ash part, because we know that in 1991, an eruption of Monte Hudson in the Andes was recorded in Falklands. They observed the fallout, so it could be an important source of ash and dust, yeah, for the Falklands.
I think we have the signature, by the way. I can check the data we have in Patagonia, but I think we have the neodymium signature of the volcanoes.
Of the volcanoes? Yeah.
I think so.
Yeah. Yeah, I know that, but I don't have the data yet, so I don't plan them yet. But they exist. So it's why we want to do neodymium, because they exist for the main volcanoes in South America.
I can tell you there are loads of volcanic eruptions, not only the Alps, but there are loads of volcanic eruptions that can shift your signal.
Yeah. Probably, yeah.
So I'm going to talk about dust deposition and carbon accumulation during the Holocene in the central part of the Great Plains grasslands of North America, where the star is located. And this is a region with historic dust storms and lots of geologic records of dust accumulation through the Quaternary. The geologic record of Holocene dust deposition in this region is actually pretty straightforward. And it's represented by accumulation of loess up to 6 meters thick at some sites like this, in what we call the Bignell loess, or the Holocene loess, separated from actually much thicker late Pleistocene loess by the well-defined Brady soil paleosol. And just as a quick aside, my collaborators and I have done lots of work on identifying episodes of Holocene dust deposition and dating them, looking at vegetation change with stable carbon isotopes and so on, and relating that to Holocene environmental change from other records in the region. More recently, we've been looking at stabilization of soil organic matter in the Brady soil paleosol, and why it's stabilized, whether it's vulnerable to oxidation, if it's exposed by erosion. My topic today is related and actually simpler than those. It's the idea that you can get enhanced net storage of organic carbon in mineral soils through Holocene dust deposition by two mechanisms. First, the Brady soil is buried and part of the organic matter in it is preserved throughout the next 10,000 years to the present. And then as the Holocene dust piles up on top of the Brady soil, plants are growing on it, adding carbon. Some of that carbon is also preserved after burial. So the idea is there's greater carbon storage than there would be if the land surface was stable and you just had an equilibrium soil carbon content. And those two effects should actually still be evident even when the Holocene dust is much thinner. The Bignell loess is much thinner at these two sites, only a few tens of centimeters. This should still enhance local soil organic carbon storage, although you would think the effect would be much less than where the Holocene loess is much thicker. And I'm going to look at that idea using data from most of the sites shown here, with symbols scaled by the thickness of the Bignell Holocene loess, which clearly, well, sort of clearly decreases downwind in the direction of the arrows from these large dune fields shown in yellow. So we can look at a really wide range of thickness, a really wide range of Holocene dust accumulation to consider this issue. And so what I'm going to look at is the net accumulation of carbon after deposition of the loess on a mass per unit land surface area basis in two ways, including the Brady soil and then just looking at the loess above the Brady soil. And I'm going to hypothesize that in both cases, organic carbon storage should increase with increasing Bignell loess thickness. More of these effects will operate more effectively as you get more and more dust accumulation at a site. And I'm also going to hypothesize that that effect of dust accumulation could actually be greater than the typical factors we look at in looking at what controls soil carbon storage, like climate or soil clay content. And there's an error here. I'm actually looking at kilograms per meter squared of organic carbon storage. Otherwise, the calculation here is almost exactly what people do to look at carbon stocks in an individual soil profile, except I'm subtracting a small baseline content of organic carbon that's actually brought in with the dust, that's in the unweathered dust at sites where it's really thick. And so working through that calculation for many profiles at most of those sites I showed on the map earlier, at first glance, the pattern is complicated. However, what you can see over on the left side of this graph toward lower loess thickness, there is a steep vertical trend of increasing organic carbon storage for the whole profile, including the Brady soil, with thickness. But then as you move into the thicker loess, the points clearly fall below that steep trend. And the same thing is evident when you look at just storage above the Brady soil. So those points that fall below that steep trend on the left-hand side have a number of characteristics. First, the loess is really rapidly deposited, so maybe not time for carbon to be stabilized before it's buried. Maybe it's turned over then faster. Also, as the color coding shows, they tend to be in the driest part of the study area, lower rainfall, so less plant productivity, less carbon addition. The points that fall on that steep trend on the left all tend to be in more humid areas, parts of the study area. In addition, all those points on the left tend to have higher clay content as in the unaltered loess, which could help stabilize organic matter as well. So just to use simple linear regression at this point, separating the points by clay content, above and below 15% clay in the unaltered loess, we see that there's two trends that are significant. One is somewhat stronger, the ones on the left, that steeply rising trend of organic carbon with less thickness, a much weaker but still significant trend, and less steep trend for the points that are in drier climates, more rapidly accumulated dust, and lower clay content. And then if you take loess thickness or dust accumulation out of the picture, just look at effects related to climate or clay content alone, there's no apparent relationship with carbon accumulation at these sites, with total carbon storage. So these results at the individual profile scale do support the hypotheses I proposed initially, but in a complicated way. The relationship is actually different for the drier sites with much greater loess accumulation and lower clay content. But this is really just at the scale of the individual profile, and we're dealing with whole landscapes. So I want to finish by looking at going from the profile scale to the landscape scale. And there's some major issues with doing this. First of all, the loess really is only preserved. The Holocene loess is only preserved on these flat or almost flat tablelands. It's not preserved on the steeply dropping slopes around the edge of the tablelands. Also, if a tableland surface is near the upwind edge of the Holocene loess, thickness of the loess can decrease drastically over only a few hundred meters. So I'm actually not sure at this point whether I can account for this in any quantitative way in terms of estimating total carbon storage related to dust deposition across that tableland. But we can deal more simply with the fact that the loess is only preserved on top of the table, shown here in a ground view now. There's essentially no Holocene dust accumulation, very little carbon accumulation at all on those steep eroded slopes that drop away from the tableland surface. And they actually make up a lot of the landscape. So I'll show you 3 examples of quantifying that landscape scale effect of loess preservation. In each of these maps, the tan color shows the area where Holocene loess is preserved based on topography, soil survey data, and our own observations. I've calculated the percentage of the total area that represents for a much larger area that I'm showing in the map here around the map. And then I'm using our data from this area to say that in this case, for example, we have 3 to 9, we have a certain estimated carbon storage in Bignell loess where it's preserved. We have, if we take into account the limited preservation across the landscape, that shrinks to a very low amount of carbon storage in the landscape as a whole. If we move to an area where the tablelands are a little more extensive, a little more preservation of Holocene loess across the landscape, still relatively thick Holocene loess. More is stored when we take into account that landscape scale preservation effect. More carbon is stored due to Holocene dust accumulation, but still significantly lower numbers than if we just look at it at the individual profile level. And then what actually turns out to be the setting for the greatest effect of dust accumulation on total organic carbon storage at a landscape scale is where the Holocene dust, the Holocene loess is relatively thin, actually less than 0.6 meters in this case, but the loess is preserved over more than half of the landscape, and that actually leads to the highest numbers, the largest numbers for total storage averaged across the landscape as a whole. So you have to look at not only the individual profile scale, but the landscape scale to get an idea of the impact of Holocene dust accumulation on soil organic carbon storage. So I'll stop with that.
Did you get an interest in nutrients concentration in the soils by any chance? Like nitrogen, phosphorus, calcium?
At the sites that are still under natural vegetation, I think the nitrogen would follow the same pattern as the carbon.
Okay.
Beyond that, I can't say anything about nutrients. Some of the sites are cultivated, some are under natural vegetation, and we haven't really looked at nutrients under natural conditions.
I will present you something about aeolian fluxes from Romania, reconstructed from peat bog. We also have dust and sand fluxes. Dust is originally from probably regional inputs, and sand is from local, and we want to see the difference between those two. The exact mechanism to do this, just 1 second please. So we have main dust sources like Sahara or Arabia, where we have a dust emission, and they are deposited in homogeneous peat bogs like the one that we have. Also, we have the sand, which comes from local sources, and together will be a part of the peat, about up to 10% of minerogenic content. Our site is located in the northern Romania, and for comparing the data, we used other three records from Europe, and from Sweden we have some sand records. Is located in the northern Carpathians. Is a homogeneous bog. That means that raises above ground level, so we have only Aeolian input, not from rivers or streams or something like this. The geological setting of the site is compromised by crystalline rocks and sedimentary rocks, like limestones and sandstones, which are located in this part. The method used, we have used loss on ignition, geochemistry, XRF, used only the titanium from the XRF, and also the zirconium. But the main part of the study is the particle size analysis. We have two methods. One automatic and one that is manually. We counted mineral particles from at a microscope. The HD model, it's the pit bog is around 8,000 started, and we have 12 C14 dates and 10 another date. The maximum depth is 4.5 meters. Now we are going to the results. This is the manual particle size. We have particles from 100 to 1,200 microns. Mainly I compromised from particles from 100 to 200 microns. From mineralogical point of view, we have mainly quartz. The black part is mainly 90% of the minerogenic part. We have also calcite, the blue part, and another minerals like melanocrate minerals like olivine are compromised in the black part. One second. In this part, I want to show this part from 3,000 to 2,000 years. We have a lot of other minerals included in this part, and I'll show you why. Also, here you can see the maximum grain size, which we have used to characterize the wind speed from this point. So basically, if you have a bigger grain size, we have a stronger wind to carry that particles. The laser particle size showed up that we have particles from clay to sand, coarse sand, but the main part is compromised by fine silt and medium silt, which is from 3.9 microns to 63 microns. So it's very small, so it could be regional, not locally. Also, what I showed you in the previous slide is this zone, which is characterized also by a lot of sand. So in that part, we could have a lot of local input. Not we could, we sure have a lot of local input in that part. Also, we have the titanium concentration, which can be seen here, and increases in the same time with the sand. Also, all the bars represent events of high dust fluxes recorded in our study. You can see here that part with a lot of sand. In the same time, the dust flux is increased, and the titanium, and we think that the titanium great concentration comes from the sand and not from the dust. We have calculated the dust fluxes and the sand fluxes by two methods. The sand fluxes are calculated from the titanium and also from the particle size. And both show the same trend in time. The sand fluxes located here, and one is from manual particle size, and one from the automatic particle size. As an overview, from 8,000 years to almost 4,000 years, we have low dust fluxes, but increased sand fluxes from local source areas. From 4,000 to 2,000, we have both increased sand and dust fluxes. And in more recent times, we have low dust fluxes and sand fluxes also. But we have some increases sometimes, like in the medieval climate anomaly. In the last years, we have enhanced dust and sand, showing that anthropogenic, that human activity have influenced a lot the composition. We have compared the fluxes with depth water table, which shows if we have a dry or wet, if it's dry or wet, and also the isotopes of C13, and also the percent of trees. And we can see that in general we have more aeolian influxes during wet periods and not dry periods, which is strange. Surprising. But also we have enhanced aeolian influxes during drier periods. And in this drier period, we can see also that is the period with the sand content, and does not agree with the other ones. If we compare with other records, we can see that in the bottom part, we have some peaks that are the same in Belgium and also in Switzerland at 6,000 almost, at 4,000 and at 3,000 years. But in the most recent years, from 3,000 to present, we have a similarity between the records, and I will show you here. So in Poland and in Romania, you can see here that we have the same conditions. For example, here it's wet here, and here it's dry. But the fluxes are inverse. So when we have high influxes in Poland are reversed. As a conclusion, we have a high variability in dust fluxes over the last 8,000 years. It's primarily linked to climate change. We have dust fluxes enhanced in the last 200 years, and our record shows similarities and differences compared to other records of sand and dust fluxes.
You presented two categories of grain sizes, so the fine one and the coarse one. What is the proportion, if you take the total number of particles, what is the proportion of fine particles, like around 10 microns, compared to the entire range?
Lower, we have around 80 to 90% finer particles, and about 10% larger particles. But the larger particles have more concentration of titanium, for example.
Okay, yeah. And do you have an idea, is there, maybe I missed it, there is a local source for the coarse particle?
Of course. Okay. We can't have particles, larger particles from regional. Maybe 1-2 kilometers, that's a maximum for sand particles.
Which is then very surprising to have more of those particles when it's wet.
Yes.
You also have more of these particles in the last 200 years.
Yes.
So
both sand and dust.
Yes, but the dust can come from very far away, whereas the sand comes from very close. So do you know how the landscape has changed? I mean, you say it's anthropogenic effect.
We have a lot of deforestation in the last years. And also, I forgot to put, but we have the fire regimes from this side. So every time was a high fire activity, we had more sand influxes. So was a lot of erosion, and we had a lot of sand from local sources.
I'm going to present you a reconstruction of dust sources in the far eastern equatorial Pacific, that is between basically 85 and 90 degree west, and over the last 30,000 years, so a little change in the scale. First, I'm going to present you a bit of background on the area. The far eastern equatorial Pacific is characterized by a meridional shift of the ITCZ, as exemplified by these two maps of precipitation over the area. So in summer, what you can see is that you got the ITCZ in its northernmost position, around 10 to 12 north, and you got rather intense precipitation, especially above Central America. In winter, the ITCZ migrates south. You got strong northeast trade winds, and especially above Central America, you got these strong wind jets that cross over the topographic low. And you can see that Central America is becoming mostly dry during this period, except for this area. What's about the past, actually? During the past, we know that there are meridional shift of the ITCZ. The problem is that, especially in this area, we don't know the amplitude. So depending on the publication, that goes from like a couple of 1 or 2 degrees to up to 6 or 7 degrees. And even the direction is not certain. So what we did, we looked at the dust sources to try to reconstruct the provenance of dust and hence the atmospheric circulation. One remarkable feature about this area is actually that even the main sources of dust are largely debated over the entire area. There are mineralogical data from dust samples collected on board some ships quite a while ago that say that basically dust is coming from western and southern Mexico. Models, however, tend to agree that North Africa is the main source of dust to the area, even if South America could also be a contributor. But one thing about the models, they are very interesting, but they can't take into account the local sources. For instance, like North Africa is...
That's done for this. No,
That's
it's
right. North Africa is a big patch, and actually Central America is not even a specific area. So we're going to look at the variation of the dust flux, the dust sources, the dust relative contribution, the relative contribution of the various sources over the last 30,000 years, and I'll focus on Heinrich Stadium 1. And the ultimate goal will be to reconstruct the shift in the ITCZ. So for that, we use two different sediment cores, ME24, which is located right on the equator around 86 degrees west, and another core which is TR19, which is slightly north, about 2.2 degrees north and 90 degrees west. What we did on the sediment is that we used we wet sieved the sediment using the below 63 microns fraction of the sediment, and we did some sequential leaching to remove the carbonates. So removing the carbonates using buffered acetic acid, and also removing the ferromanganese coatings. So in the end, we got the heterogeneous fraction below 60 micron, and as we're far from the continent, and also because we got some grain size analysis, we can assume that this is mostly dust we're looking at. And then we used lead and neodymium isotopic composition as a diagnostic tool for the dust provenance. So here are the results. The upper section is ME24, lower section is TR19. In red, you got the variation in lead isotopic composition. In blue, the variation in epsilon neodymium compositions. And in brown, you got basically that's the 232 thorium normalized flux, which is a proxy for dust inputs. And what we can see here, especially in ME94, is that you get this great increase of dust during, well, basically, between 17.5 and 15,000 years. So that corresponds to HS1. And when this increased dust is occurring, actually you can see that there's a great decrease in the epsilon neodymium composition. You go down to -4, and you get an increase in the lead isotopic composition. Prior to this, you get very stable isotopic composition, which means that you get very stable sources of dust during this entire period. After that, it's slightly different. There's not much lead data here, but it's still rather stable compared to what is happening during HS1. For TR19, on the lower part, the dust peak is much broader. Actually, it starts about the same time, ended up at 13.5. And actually, there's no correlation with the lead isotopic composition. Actually, what happened is that when the dust starts to increase, the amount of dust starts to increase, there's a decrease in the epsilon neodymium and a decrease in the lead isotopic composition. Now, to look at the different sources, we can use lead isotopic compositions. So that's a graph of 208, 204 versus 206, 204 lead. But you can also look at the neodymium composition versus lead and try to decipher which are the different end members on mixing lines. And actually, MA24 is right. It is quite nice because you got two end members where actually all the points are that's the blue points are aligned on a line, which means that you basically have a mixing between two different sources. One interesting feature is that actually the radiogenic end member, the radiogenic source, appear to be the same as for TR19. You can also see this in the neodymium versus lead plot, and you get and during so that's what happened during HS1, and during the Holocene you go to a very more unradiogenic end member, with especially if you look at the point here at 7.6 thousand years. TR19 is slightly different. It seems that there are at least three sources contributing. A source contributing during the early MIS2 that you can see here as well. Then you get this isotope peak that you can see here as well, which corresponds to what we see also in ME24. And during the early to mid Holocene, it goes down to values which are similar to what, or on the same line to what we see for ME24. And this is also a cluster of points here. So based on that, we can try to compare our data with various lead and epsilon neodymium composition from the literature. First of all, I try to eliminate Galapagos. We are very close to the Galapagos, so we wanted to remove any possible contribution from the Galapagos. Galapagos are plotting here. Our samples are plotting around here. So we can pretty much be sure that Galapagos is not really contributing to this area. I can also remove Australia, which are the brown diamonds. Asia, not that we were really thinking that Asia was contributing to the area. And we can exclude most of North Africa, except for these points here. These points are very specific. These are the Bolyai Depression, one of the main dust sources in the world. And actually, these are rather new data, so, and you can see it's very radiogenic. So it could be somehow the end member around here. In terms of local sources, I can pretty much think that the Mexican volcanic belts, I don't have any dust samples from there, but Mexican volcanic belts could be the unradiogenic end member, as well as Central America. You only got Northwest Central America, so Southeast Central America is globally plotting around here along the same line. We can also have Andean sources, and actually one potential candidate is the Southern Central Volcanic Zone, which basically encompasses the Atacama Desert, which could be a good source of dust for the area. So to try to remove a bit more sources, because we still have Bolivia, Central Mexico, Central America, and the Andes north of Patagonia, we can go to the neodymium isotope ratio versus lead isotopic ratios. Here in these plots, you don't get lines for mixing, you get hyperbolas, as exemplified by these trends here. And what you can see, so the data from ME24 are the blue dots, the triangles are tier 19. You can see that they can pretty much align along these hyperbolas. And based on this graph, I can basically remove the Andes as a potential source, because for a given epsilon neodymium, you're really on the unradiogenic side of the lead isotopic composition. So that would be on the left side of the graph. So it would move everything to the left side, and I don't have any sources around here. So basically, I'm only left with two different sources. So local sources, which are Central America and possibly Southern Mexico, and another source, which would be a far source, which would be the Bolyai Depression in the Chad area. Based on these hyperbolas, we can also calculate the relative contribution of each source. Right now, that's the Holocene points here. Sorry. Holocene points shows that basically you get something like below 10% contribution of the Bolyai Depression during the Holocene, so that's a very small contribution. But during HS1, it's going up to like 45%. So there's a great increase in the contribution of the Bolyai Depression during Heinrich Stadial 1s. We have modeling results that show that maybe Bolyai is actually a great contributor or greater contributor during this, during Heinrich Stadial 1. During Heinrich Stadial 1, here are some simulation from the IPSL PM5 model showing that so it's shown as an anomaly between the pre-industrial and HS1 for winter. And you can see that there are stronger zonal winds to the west. So red is towards the west. So enhanced zonal winds towards the west, especially above the Atlantic. So that's a good news because you can transport more dust to this area. You get also drier conditions over the Bolyai during this period, which means that more dust can be airborne from this area. And the Far Eastern Pacific is actually showing here on this graph, you got the precipitation, and you can see that basically the ITCZ is moving southward. So, and if the ITCZ is also moving southward, it would mean that more dust from this northern hemisphere component can come to this area. So the mechanism we propose for that is that we got a contribution of a local source over the time and a distant source which is contributing at present time. Present time would be mostly a contribution during winter when we got these Armatan winds which are blowing over the Bolyai Depression, and they are blowing towards the west, which is what we want. And we got also strong or stronger northeast trade winds during this period. Quite interesting, mid-Holocene, you got this point, especially in ME24, where you got a very reduced contribution of the Bolyai, below 10%. Well, based on the calculations, that would be more or less nothing. And no surprise, this is the African humid period, and the Megalac Chad is actually full. During Heinrich Stadial 1, you got the same mechanism, but the contribution of the Bolyai Depression is much higher because you got drier condition over the area. You got much stronger westward winds, both locals and over the Atlantic, and you got a southward shift of the ITCZ over the far eastern equatorial Pacific. And prior to HS1, you still got the two sources contributed more or less at the same rate. Bolyai is contributing more than now, so it means that you got also more dust from Central America, and it's mostly because of stronger winds. So I can't show the model results, but that's what we got also from model results. So to conclude, we have identified two different sources for the area. main contributor would be Central America and possibly northern Mexico. We got a very distant source, which is the Bolyai Depression in Africa. Both are mainly active during winter. And actually, the cool thing is that it does reconcile models and data. We got increased dust flux during the Heinrich Stadial 1 and a greater contribution of the Bolyai Depression during this period due to dry local conditions, more intense westward winds, and southwest shift of the ITCZ over the area. Thank you.
Did you match your record with records from the tropical North Atlantic with dust record from the tropical North Atlantic? So the Heinrich 1 peak should be visible in the tropical North Atlantic dust records as well, so it could prove your hypothesis.
No, I haven't done it. Most of the dust records I've seen from the Equatorial Pacific are too low resolution to distinguish the Heinrich Stadial 1. The only good thing is actually, I think it's this one. Yes. So that's not a dust record from the tropical North Atlantic, but from actually North Grip. And you got, well, there's a pretty good match between the variation in the isotopic records we got and this increase in dust in the North Grip record. But yeah, I'll try to find some more records to match the hypothesis.
Thank you.
I'm curious about how do you calculate the proportion of contribution of different sources to your study design? Could you explain a little bit?
That's a rather simple calculation. You have to have like the isotopic composition and the amount or the concentration, the average concentration in your potential dust source. And right here, it's based on literature data once again.
It's a mass balance, basically.
Sorry?
It's a mass balance.
It's mass balance calculation.
Yeah, I know it's a kind of mass balance, but it's like you have several proxies to, like, you need to consider different proxies to have your mass balance.
I can do this based on only lead isotopes, or also based on epsilon neodymium and lead. But you can do it on like only epsilon neodymium if you want.
There is one point I was thinking is like if you calculate with based on the lead isotopes, are they different from the ones of the result you got from the neodymium?
No, they are the same. Well, cool. within errors, they are the same.
Okay, thanks.
Do you know if there's any change in clay mineralogy or something like that during that peak in input from the Babes-Bolyai Depression?
Yeah, that's something we're going to look into. There are already some results that have been published by Bista et al. In 2016 or 15. Time's fast. So yeah, I need to look into this to see whether we got also some mineralogical variations in the core. We got some grain size changes. Very small, but we can see that there's a bit of change in the grain size.
I have a little bit different kind of approach to dust as the previous presentations. So I'm talking about dust as a light-absorbing impurity. So here's the nice picture made by DICE. So just to let you know that what I'm talking about is this part of the effect of dust. So the albedo effect on glaciers. So as we all know, the Arctic has warmed twice as fast as the rest of the world during the last 100 years or so. And this is mainly thought to be caused by the decrease of the reflectivity of the area due to the melt of snow and ice and associated positive feedback processes. So thereby, any process that affects the reflectivity of the Arctic will have a strong climate effect. And black carbon is a light-absorbing fine particle produced by all kinds of incomplete combustion of both natural and anthropogenic sources. It is such strong climate warming efficiency because of its black color and its surface characteristics. So globally, black carbon is actually the second most important climate warming agent after carbon dioxide, even more important than methane. And now, as mineral dust is also partly a light-absorbing particle, the question is how important is dust in warming the Arctic. So actually, the warming efficiency of these light-absorbing particles is even more amplified in the Arctic compared to the rest of the world because of their deposition on the high reflectivity snow and ice. So clean snow will actually reflect most of the incoming solar radiation back to space without any heat absorption, but when you have any impurities on the snow and ice, it will cause heat to be absorbed and the hastening of melt or ice and snow. So actually black carbon might be even more important for the warming and particularly melting of the Arctic than greenhouse gases. And the question remains, how significant is dust? So as most of you know probably, dust acts as a light-absorbing impurity, but also as a scattering impurity in the atmosphere, so it can have also cooling effects. But when it's deposited on snow, it always has, no matter what kind of dust is in question, it always decreases the albedo and is thereby a warming agent. Although black carbon has actually 100 times stronger warming effect per unit mass than dust, dust is considerably more abundant in the environment, also in the Arctic, than dust, and thereby it might have a stronger effect on the albedo of the area than black carbon. And now here I'm presenting some previous work we have on black carbon records in the Svalbard ice core for the last 300 years. And actually these type of records are really scarce in the Arctic still, so black carbon has been researched only since the 2000s or so in more detail. So there is this one record from Greenland ice cores by McConnell et al. Showing that the black carbon concentrations and deposition has increased significantly around 1910 and decreased after that, and has reached almost pre-industrial levels since 1950s. So then we had the first ice core outside of Greenland, so from Svalbard, shown here, and both the deposition and the concentrations of black carbon show the same peak around 1910 as the Greenland ice core, but a very pronounced increase in black carbon deposition since 1970s. So this is a case for a presentation of its own to discuss the differences, but the question is also that, of course, this black carbon has significantly increased the climate warming, or may have increased the climate warming in this particular area during this time, but what about dust? But in any case, our method to study this black carbon was this so-called thermal optical method, where we have these filters. We have melted the ice through these quartz fiber filters, and then this filter is put into an instrument that heats the filter to first in a helium atmosphere to volatilize the organic carbon away, and then in an oxygen atmosphere it volatilizes the elemental carbon, which is the black carbon here. And yeah, so it can quantify the black carbon, but when we took the filters out after the analysis of black carbon, we saw some nice coloration on the filters staying there. So this is a blank sample here, but otherwise you can see quite different kind of colors there, ranging from brown to yellowish, even pinkish or grayish, that has left there. And this is actually mineral dust. We have looked at it on microscopes, and yeah, it is mineral dust. And of course, you can see already from these filters that it has a light absorption efficiency, this dust that is left on the filters. So it must have had some effect also in the ice core or on the glacier. So we wanted to figure out how big this light absorption was. So there are, of course, methods to really quantify the dust on the filters, but we were actually more interested in the fraction of the light absorption it causes. So thereby we measured the light transmittance through the filter both before this thermal optical method and afterwards, and there with a soot absorption photometer, particle soot, and thereby we found out really the fraction of the light absorption caused by the dust. So we don't have a record for the last 300 years yet, because we have little material from the ice core left and we are not sure what we want to do, but we anyway tested a few samples, also snow samples from the same glacier, showing that actually 50% of the light absorption on these filters was caused by dust. The range was quite big, from 0 to 70% or so, but it definitely is a lot, and surprisingly a lot. But this number compares quite well with previous results of 30 to 50% of light absorption in Arctic snow being caused by non-black carbon constituents. So anyway, we also have this melt index record from the same Svalbard glacier. It's shown in this above figure. So the melt index is based on two ions, sodium and magnesium, percolating at different speeds through the snowpack when it's melting. So, and this is a very precise rate, so it can be reliably assessed. And this shows that, yeah, for the first 200 years of the core, nothing much happened. Then in the last 100 years, there were some quite big differences, and a sharp increase in the summer melt of the glacier since 1970s or so. And here you can see a decrease in the melt index, but this is actually not what has happened, but it's that the melt index has failed because the melt is so strong. So thereby the melt is actually still increasing at the glacier. And then there is the measurement of atmospheric temperatures at the Svalbard airport since 1911. And you can see some nice correlation between the temperature and the melt index there. But the fact is that since the 1960s, when the temperatures have increased in the area, the temperatures are still not higher than what they were around in the beginning of the 20th century. But the melt index has increased significantly. So there must be something else happening as well. Not only the temperature is causing the melt. And when you compare it with our black carbon record, well, you see that at least the black carbon has increased at the same time. So there might be something happening there. But globally, actually, it has already been stated that glaciers are melting at a faster rate than expected solely due to observed climate warming. So this is both in the Arctic, in European glaciers, and in the Himalayas. So there definitely need to be some additional factors decreasing the albedo of the glaciers and hastening the melt. So these are these light-absorbing impurities such as black carbon and dust, but also algae. And with dust, it's the extremely interesting point, as all of you probably know, dust is a nutrient for algae growth in oceans, but it's actually also a nutrient for algae growing on snow and ice. So only very recently a few studies have been published on this. There is some green, red, and brown algae growing on glacier ice when it's melting, and on snow as well. And it decreases the albedo significantly. And for example, in this case, Lutz et al. Found out that the overall decrease in snow albedo by this red pigmented snow algae blooms can be, during the course of one melt season, even 13%. And this is a huge number, because for black carbon, for example, it has been, well, the estimations are, let's say, around 5%, and for dust also around 5%. So these algae alone are really decreasing the albedo significantly. So the question now remains, what will happen for dust in the future? Well, it is expected that the dust deposition in the Arctic will increase in the future because the snow cover periods are shorter and the glaciers are retreating, so that there is more bare ground there for the dust to arise. And in the Arctic there are really strong winds, of course, and no vegetation, or not much vegetation, tying down the dust. So it's expected to increase. And as this albedo effect of these light-absorbing impurities is really huge, they should be really better included in climate models and glacier mass loss predictions. And they haven't until yet, because as I said, this is a quite new research area. So yeah, that's all. Thank you.
When you estimate the relative effect of mineral dust and black carbon in the light absorption, you're working at a specific wavelength. I mean, it's in the visible part of the spectrum, or
yeah, 500 something nanometers. Yeah.
Because probably there is the effect of dust is much more important at lower wavelengths. And
yeah. Yeah, we are only starting with these measurements, and we have a lot to learn still. So we are working at 523 nanometers wavelengths. So yeah, it is important to look also at different wavelengths. That is very true.
Yes, another question right there.
Really interesting talk. At least in North America, in the last glaciation, there's a potential for lots of dust deposition on the southern parts of the Laurentide ice sheet. And I can't recall where, but I remember some speculation about that changing the mass balance of the ice sheet at least slightly. I don't think that's based on anything beyond just speculation, but it's an interesting idea.
Yeah, it is. And the fact is that also this black carbon is actually hydrophobic. So when the snow starts to melt or glaciers melt, it stays on top of the snow and accumulates there. So even I have read a paper where someone has described that when they are on top of Mount Everest, or not necessarily on top, but in the area, they just see that the dust is settling and the whole slope is turning to gray and brown within a week. So the albedo effect the albedo can decrease by 20% in just a week because of this deposition. And you know, there are of course these dust storms, and it's sudden things that happen and can have a huge effect.
I'd never thought of this algae thing. That's very interesting, especially when you think about glacial interglacial changes.
Yeah.
So, is there any way to quantify, like if you have done? Is there any way to make a first order relationship that we could include in models? You know, like when you have so much dust, if you are at that altitude, like how does it depend on altitude? How does it depend on the distance to the sea? Are there any? Do you know anything about that? Maybe.
What was the question? How much dust there is? Or
no, how much algae will grow on the glacier? How does it depend on distance to the sea? How does it depend on altitude? Things like that.
These algae are not my field of science, but yeah, they are everywhere. But I assume they are closer to, not on top of the Greenland ice sheet, really in the middle, but closer to the seashores, because that's where you have the most melting. But actually, they appear within a week, and suddenly you have a huge plume